Today, in these lectures, we are going to study about the unit step function or Heaviside function. A unit step function is defined as u of t minus a, which is equal to 0 if t is less than a, and 1 if t is greater than a. And the graph of unit step function, it's look like a step, and it's very easy to sketch the graph. Now this is the graph of unit step function. So which is equal to 0. The function is identically 0 for any value of t which is between 0 and a, and which is equal to 1 if for any values of t which is greater than a. And if we multiply the function f of t, any function f of t, with u of t minus a, that is, if we multiply any function f of t with u of t minus a, the unit step function turns off a portion of the graph of f. So f of t into u of t minus a turns off a portion of the graph f. And it can be used to write piecewise functions in a compact form. That we'll see that some examples of functions which can be piecewise functions which can write as a compact form. Now, next is the Laplace transform of a unit step function. Laplace transform of u of t minus a. So as you all know, the Laplace transform of any function f of t equal to integral from 0 to infinity e raised to minus st into f of t dt. So instead of f of t, we'll replace u of t minus a. And u of t minus a is identically 0 for any value of t which is less than a. So the integral become integral from a to infinity e raised to minus st into u of t minus a. So a to infinity, the function is defined as 1. So 1 dt. So integrate the function with respect to t, you will get e raised to minus st by minus s from a to infinity, and e raised to minus infinity is 0. Upper limit minus lower limit, you will get e raised to minus s by s. S is greater than 0. So Laplace transform of a unit step function is equal to e raised to minus s by s. Now, if a equal to 0, the Laplace transform of u of t, which is equal to e raised to 0, that is 0 by s. So u of t, the graph of u of t is equal to 1. It's a constant function defined from 0 to infinity. It's a constant function defined from 0 to infinity. So as we all know, the Laplace transform of a constant function f of t equal to 1, Laplace transform of constant function 1 equal to 1 by s. So both the equations are same. So Laplace transform of u of t, which is equal to Laplace transform of 1, which is equal to 1 by s. Next is shifted function. So if f of t equal to 0 for all negative values of t, that is, the function is f of t, the function f of t is defined only for positive values. So for negative values, f of t is equal to 0. Then f of t minus a into the unit step function u of t minus a with a is greater than 0 is f of t shifted to the right by a unit amount a. So the function f of t is just shifted to the right hand side, the right by an amount a. So next is we are going to discuss the second shifting theorem for Laplace transform. So if Laplace transform of f of t equal to f of s, then the shifted function f of t minus a into u of t minus a, that is f of t, just multiply u of t minus a with f of t minus a, that is 0 for t less than a, and f of t minus a if t is greater than a. So the Laplace transform of f of t, if if the Laplace transform of f of t equal to f of s, then the shifted function has the Laplace transform e raised to minus as into f of s. Or in other words, f of t minus a into u of t minus a equal to inverse Laplace transform of e raised to minus as into f of s. So the second shifting theorem states that if Laplace transform of f of t equal to f of s, then Laplace transform of f of t minus a into u of t minus a. That's the shifted function of f of t, which is equal to e raised to minus as into f of s. Now let's look at an example. Write the following function using unit step function and find its transform. So f of t is equal to 2 if t is between 0 and 1, and t squared by 2 if 1 is less than t less than pi by 2, and cos t if t is greater than pi by 2. So f of t is a piecewise function. So we can write the function. So the aim is to write the function f of t by using unit step function, and we have to find the Laplace transform of f of t using second shifting theorem. So as I said, third point, we can write, the unit step function can be used to write piecewise function in a compact form. Now we are going to write this function f of t in compact form. Now f of t equal to 2 for t is between 0 and 1. That is u of t minus 0 minus u of t minus 1. So u of t minus 1 is u of t minus 0 is a function which switch off minus infinity to 0. That multiplied with 2, that is identically 0. Minus u of t minus 1, that is this function will switch the function f of t from 0 to 1, switch off 0 to 1 and switch on from 1 to infinity. So this is identically 2. It's 2 from 0 to 1, and plus t squared by 2 if t is between 1 and pi by 2, that is u of t minus 1 minus u of t minus pi by 2, plus next one cos t for t greater than pi by 2. So we have represented the function f of t using unit step function. So this is the compact form of this piecewise function f of t. Now the Laplace transform of f of t. So Laplace transform of f of t equal to the Laplace transform of the entire function. So for that, we'll find the Laplace transform of each terms, 1, 2, and 3. Now Laplace transform of the first term, 2 into u of t minus 0 minus u of t minus 1, which is equal to Laplace transform of 2 into u of t minus 0. Hereafter we are going to use the second shifting theorem. Now u of t minus 0, which is equal to 1, and minus u of t minus 1, Laplace transform of this function. Now Laplace transform of 2 into 1, which is equal to 2 into Laplace transform of 1, which is equal to 1 by s, 2 by s, minus Laplace transform of u of t minus 1. So Laplace transform of f of t minus a into u of t minus a equal to e raised to minus as into f of s, where f of s is the Laplace transform of f of t. So here f of t equal to 1. So f of s is equal to 1 by s. Laplace transform of 1 equal to 1 by s. And a equal to 1. So by using second shifting theorem, we can write the Laplace transform of u of t minus 1 equal to e raised to minus s into 1 by s. That is e raised to minus s by 2 into 2. So Laplace transform of 2 into 1 minus u of t minus 1 equal to 2 minus 2 into e raised to minus s by s. Then next is the second term, Laplace transform of the second term, that is Laplace transform of t squared by 2 into u of t minus 1, which is equal to Laplace transform of. So I will rewrite t square as t minus 1 plus 1 the whole square by 2 into u of t minus 1, which is equal to 1 by 2 into Laplace transform of a plus b the whole square. That is a square u t minus 1 square into u of t minus 1 plus 2ab, 2 into t minus 1 into 1 into u of t minus 1 plus b square, that is 1 square into u of t minus 1, u of t minus 1. Now again, using by second shifting theorem, Laplace transform of shifted function, which is 1 by 2 into Laplace transform of t minus 1 whole square into u of t minus 1. So a equal to 1. f of t minus a into u of t minus a equal to 1. And f of t equal to t square. Laplace transform of t square is equal to 2 by s cube. So using second shifting theorem, e raised to minus as, that is e raised to minus s into f of s. f of s is equal to 2 by s cube plus Laplace transform of this function. Again, similarly, 2 into Laplace transform of t minus 1, that is Laplace transform of t, which is equal to 1 by s square into e raised to minus as, a equal to 1, plus Laplace transform of u of t minus 1. That's we are already calculated that u of t minus 1, which is equal to e raised to minus s by s, e raised to minus s by s. Then combine those equations, we'll get e raised to minus s as, take e raised to minus s as a common factor into 1 by s cube plus 1 by s square plus 2 by s. That is the Laplace transform of t square by 2 into u of t minus 1. Next aim is to find Laplace transform of t square by 2 into u of t minus pi by 2. Laplace transform of t square by 2 into u of t minus pi by 2. Again, we have rewrite the function t minus t square as t minus pi by 2 plus pi by 2 the whole square by 2 into u of t minus pi by 2. Same way, a plus b the whole square, a square plus b square into 2ab into u of t minus pi by 2. Again, using by second shifting theorem, we will get e raised to minus pi s by 2, first one, a equal to minus pi by 2, then f of t equal to t square, f of s is equal to 2 by s cube. Next one, pi square by 4, then Laplace transform of 1. So here it's a constant function. So Laplace transform of a constant function is equal to that pi square by 4 into 1 by s into e raised to minus as. A is equal to pi by 2, e raised to minus pi s by 2 plus the last term pi into t minus a into u of t minus a, and f of t is equal to t, Laplace transform of t equal to 1 by s square. So pi into 1 by s square into e raised to minus as, that is e raised to minus pi s by 2. Compare this equation, combined, we'll get 1 by 2 into e raised to minus pi s by 2 into 2 by s cube plus pi square by 2s plus pi by s square as the Laplace transform of t square by 2 into u of t minus pi by 2. Next is Laplace transform of the last term of f of t, that is cos t, Laplace transform of cos t into u of pi t minus pi by 2. which is equal to Laplace transform of cos t equal to t minus pi by 2 plus pi by 2 into u of t minus pi by 2. Then cos a plus b. Cos a plus b is equal to cos a cos b minus sin a sin b. Cos pi by 2 equal to 0, sin pi by 2 equal to 1. So I can write which is equal to minus of sin t minus pi by 2 into sin pi by 2, that is 1 into u of t minus pi by 2. So here f of t equal to sin t, a equal to pi by 2, and Laplace transform of sin t equal to 1 by s square plus 1 into f of s into e raised to minus as. A is equal to pi by 2. So Laplace transform of cos t into e of t minus pi by 2 equal to minus e raised to minus pi s by 2 into 1 by s square plus 1. So Laplace transform of, so finally the Laplace transform of f of t equal to Laplace transform of this function, that is 2 minus 2 into e raised to minus s by s plus Laplace transform of this function plus Laplace transform of this function, and you will get the answer as first one Laplace transform of first component of that f of t, then second one, then the last one Laplace transform of cos t into u of t minus pi by 2, the last one. So this is the Laplace transform of f of t. Laplace transform of f of t.